So quite simply speaking, my talk will be about convincing you that relativity, in particular mathematical and numerical relativity, can teach us a lot and a lot of surprising things about cosmology. Now, I assume that at least some of you believe in cosmology we don't really need the full power of computational relativity, of mathematical relativity, for a very good reason. First of all, we got pretty far with it. We got pretty far with simplifying the field equations that I show you here. So the first equation is obviously the Einstein equation. The left-hand side is just given through the Ricci tensor, and the difference to the Ricci scalar. G is the form metric, G mu nu, and T mu nu is just a stress energy tensor. And we have to complement the 10 coupled partial nonlinear differential equations by the evolution equations for the stress energy tensor. Now, we know that for a generic geometry, for a generic form of stress energy, is a really complicated system that, especially those of you who were here in Francis' talk yesterday, he made a very impressive presentation of it, how difficult it is to make any sense of these equations, in particular to find any solution of them for a given situation. Now, in cosmology, we are extremely lucky. And that's what I believe led to the fact that we got pretty far without recognizing what kind of difficult equations we are solving. And the reason being that we have an exact solution. And our universe, to a very good approximation, looks like this exact solution as far as the space-time geometry is concerned. Namely, what is describing the universe to first approximation or to leading order is the so-called Friedmann-Robertson-Walker space-time. That is spherical symmetric. It's a spherical symmetric space-time, or as more of you know it, or most of you know it, homogeneous and anisotropic space-time, described by really a single dynamical parameter that only depends on the time coordinate t. Now, this introduces, as it turns out, an extraordinary simplification to the field equations. And this was what Paul showed you quite impressively, how far one can get when one evaluates the 10 plus coupled nonlinear partial differential equations of Einstein relativity for the Friedmann-Robertson-Walker spacetime. Now, one really ends up, strictly speaking, with one constraint equation, and the notation is exactly the same as Paul used it. So A is denoting the scale factor dot differentiation with respect to physical time, and the rows are just some initial matter density for the different components. I don't need to repeat it since you heard about it just half an hour ago. And the second equation is a true evolution equation. Some of you might know it as a continuity equation that describes you how matter goes, here given through its energy density and pressure. And again, the familiar epsilon, how you connect to a canonical scalar, is given through the equation of state. Now, obviously, my talk won't be about these equations. But why these equations are so powerful in describing cosmology is because we assume, and it seems to be working, that the exact solution that is introducing this huge simplification entails the essential nonlinearity. So it's not because we are perturbatively away from Newton. We are very far away. So space, that's what we are seeing. Cosmology, I learned it from Slava first. It's very much in the strong field regime of gravity. So cosmology is a wonderful probe of the strong field regime of relativity, or general relativity. However, because we have an exact solution that carries the essential nonlinearity, we get really far, and the last 40 years in cosmology are an impressive proof of it. We get really far just by using this fact and going only perturbatively away from the exact solution, which is the Friedmann-Robertson-Walker spacetime. However, and this is really what I want to talk about it, we should not stop here. Because, and I will give you two examples why we should not stop here. So we get very far, but in order to know how good our cosmologists are, we sometimes have to ask questions that are beyond the realm of being just perturbatively close to the exact solution to the Friedmann-Robertson-Walker spacetime. And the two questions that I will discuss, the one is when we actually explicitly know that we are not close to Friedmann-Robertson-Walker, namely when we ask how robust is our early universe scenario to generic initial conditions. And what I mean by generic initial conditions in particular, here we don't assume, oh, it's not. Do you see the, no. Then I use that, okay. So then when the metric is arbitrary, more or less arbitrary, so you want to ask how far can you get with the scenario that Paul described by presenting that having a negative potential leading to an epsilon that's greater than 3, inducing smoothing, the onus on me is to show it is super smoothing in the sense that what he has shown, note, he has only shown that if you go just a little bit far away from the Friedman-Robertson-Walker solution, so that your approximation is still good, that your leading order space-time is homogeneous, maybe anisotropic, that's what he was showing about the anisotropy being encoded into this term, then an epsilon greater than 3 is a smoother. But what we mean by super smoother would mean that for generic space-time, when you absolutely cannot apply these equations, and you cannot just simply transfer your intuition, or if it works in this realm, it has to work for generic metric. That's the real question when you ask for robustness of initial data. When I'm so far away from the metric where I want to get to that I cannot apply the perturbative analysis around this metric, how good is my smoothing mechanism? So that's the first question when we know that generically you cannot use this analysis anymore. You have to solve the full set of Einstein equations for a scalar field. And the second example that I will give is an even bigger surprise. It surprised me that sometimes when we believe we have the justification to assume this metric and compute around it and have a trustworthy solution, it might not be the case. So let's start with the first example. And this will be the only, so you will see a lot of movies in this talk, but I really believe it's important for you to appreciate the difference between what we normally do in cosmology when we don't solve the full set of Einstein equations, but simplify it for the Robertson-Walker space-time versus what we are doing when we actually solve the full Einstein equations. Namely, it's not so simple that you just take these equations, put 10 plus 1, or 10 plus 4, or 10 plus 6 equations on the computer, depending on what you assume about your space-time. Most of the time, and especially the relativists in the audience know, most of the time, it just doesn't work. So the real diffeomorphism invariance, or gauge invariance, of general relativity means most of the time you choose the wrong gauge. And what it means, really, most of the time you choose the wrong coordinate system. And there is only a very few coordinate systems when you can solve the full set of Einstein equations. That's one of the tricks, especially mathematicians in the audience know a lot more about than I do, and also those people who are trying to put it on the computer. What you really need is, because the computer, as Franz a year ago was pointing it out so beautifully, and so those of you who weren't here, please definitely watch his talk, was pointing it out, the computer is completely unforgiving if you have a system that doesn't solve the Cauchy problem, or it's not well posed. What does it mean? If you try to solve, and this is exactly what Paul also meant by saying something is classically predictive, classically solvable, that if you have a system, a classical system, you can only make predictions when for given initial data, the system admits a solution, and the solution is unique, and locally depends on the initial, continuous locally depends on the initial data. If it's not the case, then quite generically, physically, you don't have a predictive theory, but even more so, the computer immediately explores all the solutions. So the computer is extremely unforgiving of a bad formulation. Now we know, thanks to Yvonne Choquet-Bruhat, that the Einstein general relativity has formulations that are well posed. So that's great. And this is what I will be utilizing in my talk. We know that there are formulations of the field equations that are well posed, so we can, in principle, and this is what being utilized in the simulation of black hole mergers, black hole neutron star mergers, that you all are at least familiar with in the sense that you know that this is not very important topics, even if you don't yourself solve them on the computer. But what we also know is that just having a well posed formulation might not suit your physical situation. So there are two more challenges that we have to solve. We have to find a mathematically fine formulation in the sense of having unique solutions for given initial data that continuously depend on the initial data. And we have to find a formulation that is the problem that most prominently Franz solved for the black hole problem, that admits a numerically stable solution. That means that we know how to add damping terms so that the fact that the numerical evolution cannot set the constraint to 0 doesn't make the constraint grow as if they would go according to the theory of relativity. So that's a second challenge. And note that very many mathematical formulations that are well posed are not well suited for constraint damping. And the third challenge is that And this is something that is in particular in cosmologic case that is not so well probed in the non-perturbative regime. To study non-perturbative regime as black holes, we have to find a formulation that's well suited for the physical situation. And instead of speaking abstractly, I just want to tell you what the challenge is in the case of contraction. There are two particular challenges: how to pick a good, well-posed formulation that admits a stable numerical evolution. And the one is something that Paul mentioned a lot, and the second is also something that Paul mentioned a lot. So the one is that if you don't assume anything about the bounce mechanism, and for slow contraction we don't have to modify relativity, you know that the theory has a singularity. And the computer is such that if there is a singularity a finite time away from where your initial data is, the computer tends to immediately drag you down there. So what you have to find is a formulation where a singularity is infinitely far away from your initial data. So that is literally you have to evolve infinitely far so that you find the singularity. That's a technical question that represents the physics faithful. And the second question, or the second problem, was really the content of Paul's talk. We have two scales in the problem. The one scale is the scale factor. And as he has presented it, the scale factor hardly changes. So the scale factor really explores the 1 or 2 or 3 orders of magnitude of changes. But we have another scale that changes extremely rapidly. And this is the scale of the 3 curvature. This is the Hubble scale. And those of you who, and probably most of you, who had differential equations maybe back in high school or college, know, or later you work with them, know that this is something that leads to a really, really bad stiffness problem, right? You have different scales in the theory that if you leave all the scales as they would physically evolve, then they would immediately crush you. So you not just have to solve the mathematical problem, the simple evolution problem, of numerical damping, but you also have to find a formalism, and this is the so-called orthonormal frame formalism, that using Hubble normalized variables, that again, I don't want to be redundant and just refer to Francis' talk from last year. The only thing what I want to point about the feature of this formalism is it fulfills all the criteria. The singularity is infinitely far away. It's well posed. It fits well the initial physical situation because we cheat. The system, the evolution equations don't see the Hubble parameters since everything is Hubble normalized. And therefore, and this is the reason why it stays sufficiently, for a sufficiently long time stable. As a matter of fact, I should mention it immediately. Everything what I will show you will be 120 e-folds of contraction in the Hubble parameter. So exactly corresponding to the scenarios that Paul was presenting just here non-perturbatively. So once you have this all set up, then you can do numerical relativity, and you can solve the full nonlinear set of partial differentials, which are the field equations. Now, just to see how impressive it is, remember, we worked with, to elaborate the scenario and to present it to you, we worked with a single constraint and a single evolution equation. And notably, for the exponential potential, this is an exactly solvable system. We know that. This is the famous scaling solution. So we not just can represent the system, we know what the outcome is. So it's just 2 ordinary differential equations, very simple to solve. But we end up for the computer will be a set of 26 in this formulation, 26 coupled nonlinear partial differential equations, and 19 constraint equations. So I'm emphasizing it because what you will be seeing the next 40 minutes will be simple curves. Simple curves that you think, oh, there is not much behind it. Everybody can do it with mathematical. So I just want that you remind yourself when you see these curves and think this is simple. This is not. This is just as complicated as solving a merger of 2 black holes. This is the same set of complications in the equation that go into it. You are very far away from being anywhere perturbatively close when you start perturbatively close to the exact solution, which would be simple. So, and just to illustrate it without mentioning and explaining you the variables, here is a system that describes neither metric. For the expert, it's a very interesting system since it's a coupled system of one elliptic equation, which is describing the evolution of the covariant generalization of the Hubble parameter in some sense, the scale invariant lapse. You can also think of it as your covariant and gauge invariant time coordinate. And we will have 5 equations for the evolution of what we call here in the good tradition of relativist matter. But we talk here about, of course, what we consider matter is scalar field matter. Just so what to watch out for, this is here what represent, roughly speaking, the sigmas, the anisotropy contribution, fully non-perturbatively. And these terms are, again, describing the metric and more or less going into the spatial curvature terms for the purposes of understanding this simulation. And here are the constraint equations that have to be fulfilled and checked during the evolution. Obviously, you see, maybe you can recognize that this is the equation that was our so-called Friedmann constraint, non-perturbatively. You can recognize it, for example, seeing that this is here the scalar field energy, and here are all the metric components, and they all have to sum to 1. That the fact that they have to sum also tells you we are in a Hubble normalized system, so everything is, in this sense, dimensionless. So far, so good about the theory, and if you feel now, oh, this is complicated, that's good. That's everything what I wanted to communicate to you. It's not simple. We cannot guess what the solution of this system is for an arbitrary initial data. And this is important. This is important because people think, oh, if we solve the Friedmann equations and we know what the solution would be perturbatively close to the Friedmann equations, then we know what to expect from the nonlinear analysis, from the fully non-perturbative analysis. But if you look at these equations, I bet nobody knows what to expect. Nobody should know what to expect. Just because it will something will come out that you might have expected. It's not happening for the reason because you have shown it for the system. This is a surprise. And if it's coming out in the same way for arbitrary metric, that indicates robustness to the initial data. That's extreme robustness to initial data. So what means to robustness of initial data, that the system for arbitrary metric should behave, or for a large class of metrics, should behave as we would have thought it behaves when we are very close to the solution that we want to get. Okay, so I wasn't the first one who was involved into this study, and quite impressively, the first study that asked how robust slowly contracting a universe filled with scalar field matter, that if considered as a fluid has this super stiff large equation of state with Paul was denoting by large epsilon, so epsilon 60 or something like that. It can be just greater than 3. Then we have, at the end, we end up dynamically with a Friedmann-Robinson-Volker system. It was studied by David, who is sitting here in the audience, Wojciech Lim, then graduate student, I believe was at my current institute, the Albert Einstein Institute, Franz Pretorius, and Paul. And Franz was talking about this, so I just want to remind you of one thing because it will be relevant. What is the philosophy of most of the simulation that we are doing, and then where does one go next? So first, when one starts with a simulation, typically, just to save computer power and know where we are, one takes the simplest possible configuration, but not simpler. And the simplest possible configuration here means you assume some symmetry in certain spatial direction. And what you see here is that it's a simulation where we assumed that all inhomogeneities are depending only on one spatial direction, one spatial coordinate. You can think of it as an x-coordinate. And the y and the z coordinates don't contribute to inhomogeneities. Which is a simplification, and we will leave this simplification in a few slides, but it's a good simplification for 2 reasons. If this doesn't work, you don't have to go further. If you assume symmetry and you already don't find robustness to initial data in the sense of inhomogeneities one direction already would tell you that for generic initial data you don't converge to Friedmann-Robinson-Volker, then you can stop, then you can say you have lost. Of course, if it shows that it's fine, then you move on. Assume less symmetry, maybe add in different type of matter, maybe add in more realistic conditions. So let's see what, and we know from last year what they have shown is if you now evolve this system and the curves representing these Hubble normalized energy densities, so what you would be usually considering as the so-called omegas in astrophysics, so the fractional energy densities of yellow will be scalar field matter, so the phi field, while it contributes to the energy density, again, non-perturbatively. Then blue is spatial curvature. It corresponds, again, to this so-called k over a squared term from the Friedmann equation. Of course, it's, again, a nonlinear covariant generalization of it. And you have up there, the contribution that Paul was referring to as your worst enemy, this is the shear contribution. And notably, those of you who work, and this is most of you who work on inflation, would never be worried about the shear, right? Because you know that exactly for the same reason that Paul presented is, shear is the one that in an expanding universe you would expect dilute fastest. But here, because we are contracting, because if you remember, shear goes like, even in the simplest deviation from the Friedman equation, Friedman space-time, the so-called Kasner space-time that Paul was presenting, and we will get back to that in a second, already there, shear goes like 1/8⁶. What means is that you have to really watch this component, and then non-perturbatively what it tells you, add in the craziest shear component that's possible. That's the worst initial data. I mean, you can try it also, of course, with curvature too, but you won't be surprised that will lead to a Friedman-Robertson-Walker universe. So what it would mean is I probably test, and you have to do everything, but that's why I'm showing you the shear. I probably test the robustness of my mechanism to initial data in the best possible way if I take the craziest non-perturbative generalization of the component that already in the perturbative limit was dangerous. And this is the shear component, okay? And that you see already, and I will tell you how unfair they were. So this is probably one of the worst and least fair initial data that you can assume that was in the literature for 12 years and still is, because we owe you the paper to come out, but I will show you the simulations and explain why this is approximately the worst possible situation for any contracting phase that you can have. The first thing what will come out, you will see, is space-time, if you evolve, and again, you have several tens of e-folds evolving here. This is the early simulation. This is exactly the simulation that appeared in the 2007 paper, and Franz was also describing in much greater detail than I do today. But what you see is, as a result, there are two, so at the end of the day, the universe in a box is split into two different regions. One region looks just fine. Shear and spatial curvature don't occupy any fraction, or virtually zero fraction, of the energy density. And the scalar field matter, this phi field, this super smooth energy density dominates most parts of the universe. And I will tell you why most parts. In fact, before I explain you what the bad region is, I can tell you that we can measure most parts by saying that if we measure the covariant generalization of a good volume measure, which actually normally is given in the perturbative limit in terms of H inverse, now I told you that the scale invariant lapse, or n, would be the generalization of H inverse. What you see is large n means then small volume. Okay? And so this region that looks weird, where shear seems to dominate as a result of the evolution, this occupies very little volume because it is associated with a large lapse, which means very little proper volume. So that was the conclusion. This is just really the recap of where we were a year ago when we started to look at the phases, that it looked like that if you start with fairly large shear with some weird field configuration, then you still have your entire universe non-perturbatively converging to a smooth space-time. And so I just want to remind you, when Franz said last year, this is established that this is a very robust smoothing mechanism. And that's what we meant by it. Now, let's look a little bit at this region, because what we asked ourselves, and here in particular I should point to Will Cook, who joined the collaboration a year ago. So he has a lion's share of this project. What we asked ourselves is, well, okay, this paper presented that if we assume really bad initial data, most of the volume still converges to Friedman-Robertson-Walker. But then the next question what you ask, especially in relativity, and those of you who were yesterday in Princeton and listened to Igor Rodnyansky's talk then you ask is, how generic is this messy? For a second, let me call it just messy behavior. So what kind of initial data leads to a condition that space-time ends up splitting into these two regions? One is this region, doesn't look that good, where shear dominates in a particular way, and then most of the region being smooth. Because if it's a peculiar feature, then you are better off than you thought. Because that means that for most initial data, you don't end up like this. And this is the question of how generic is the initial data that they studied? How robust is actually contraction, slow contraction to initial data? How robust is, what is the set of initial data that actually lead to these parts of space-time still being messy? And this messy is something that I won't talk about too much. It would also not be too appropriate for me to talk about it, since there are lots of experts in the audience who worked on this phenomenon quite extensively, among them Beverly Berger and Thibaut Damour sitting here. This is the so-called mixed master phenomenon. This is what you would expect in a contracting space-time that occurs. And certain regions exhibit this mixed master behavior. And again, this is this nice adaptive mesh refinement. Using adaptive mesh refinement, showing you France's simulation, you can see the Ijjas illustration, how it looks in those regions, how this mixed master behavior looks like when you simulate it. Now, the only feature for Na is a very interesting phenomenon. So again, if you're not familiar with it, please read Beverly's and Thibaut's paper for sure, and we are ourselves working on it. Very interesting, mathematically, physically, numerically, but there is one feature of it, and this is the only feature what's important for this talk. It's not something we want to have, okay? It's bad, because this is not how our universe looks like. So we ask it, what is the initial data that leads, and this is what Via was exploring, what leads to these conditions. And so I show you something that's not yet published, will be published soon, but I show you what he found. So the finding is for most initial data, you will see this. Again, how do we start with? We start with large shear again, so really large shear. So again, crazy shear. We didn't change anything about putting in the worst possible geometrical conditions for contraction to lead you to a smooth Friedman-Robertson-Walker universe. We put in some weird matter profile so that itself is not smooth over space. So again, this is a one-dimensional simulation yet. And we put in also some spatial curvature here being red. And so for most initial data, this is what we found. Oops. That's nice. So of course it will be boring, right? I can run it 120 EFOs, but I can just talk about it, tell you nothing will happen. So what we have found is that, and that's what I said, it was a freaky initial data that was assumed in the 2007 paper. There was something assumed that if we don't assume, generically, we avoid mixed master behavior. Or at least in the sense generically that physically, that condition that we assumed corresponded to a large upward velocity of the scalar. So what we have figured is that in the Lim paper, of course they presented that, what you find is that what they assumed was a scalar field that had a large perturbation moving uphill. Of course, classically, this is a freaky initial data, right? Not a little bit being delayed and moving uphill. Really, you had to give it an initial upwards kick on the potential, this exponential potential, where the scalar field would naturally skyrocket down and picking up kinetic energy. So you had to give it uphill. And obviously, this is a rare initial data, right? For any initial data where if you give the field a lot less or no uphill behavior, obviously, it's almost immediately smooth. But what really happens is you can even quantify it, and that's what we will do when you will see it in the paper, that you can quantify it now. What is the set? And really just the one thing that you had to change is no uphill, no large, unreasonably uphill kick to the scalar field. And then everything is smooth. Absolutely everything is smooth. So it's a lot more robust. So when we figured this, then Franz reacted and said, oh, this is actually lucky that it worked out at the end, because we really assumed the worst possible initial data. So it looks, or at least what we think is among, at the very least, so I know there are mathematicians in the audience, so I don't know what is the worst possible, but it's certainly among the worst possible initial data to give a huge upkick to the field, have large shear contribution, and very inhomogeneous initial matter density contribution. And what even it led to is that most of the space-time was fine, but you had mixed master behavior in some parts of space-time with small proper volume. But what we have found is if you don't give this huge upkick, then almost immediately everything smooths. So that is real robust. So, I think it's not important what you work on, what your favorite model is. I probably won't convince many of you that this is what you should be working on, but you should acknowledge this is very interesting. So that's not a problem if at the end of the day you walk out, well, okay, I still go back and do my inflation calculations, but this is damned interesting. So it's worth looking at. It's so interesting. I mean, I'm really excited about this because this is something I would not have expected. We would not have expected when we looked at it. Okay, and just so you give an illustration, what is the initial scalar field profile? This is this wide. So, because there was a question coming up, and that's why Paul was pointing to me. You see, the mean value would be around minus 0.2 where the scalar field is. And we have fluctuations that are way beyond what you could call the perturbative limit. So not just the shear is very far, not just space-time geometry is very far from the perturbative limit, we have also a very, very different scalar field profile than what we could call being close to using the perturbative limit around Friedman, Robertson, Walker. Okay, and I was telling you once something works out really well, and this is again, I have to point to Will. This is also mostly his work, to lift the code and see, well, what happens? Again, we cannot know what would happen if we had the second dimension. Now, we have a good intuition for what should happen from fully non-perturbative analytic studies. Again, I have to point to people in the audience here. Namely, this is the so-called ultralocality of a contracting universe in approaching the singularity. Ultralocality means that typically what you expect is as you approach the singularity, then what happens is the gradients become more and more unimportant. So what you would expect is that if you just assume and look at the one spatial dimension having inhomogeneities and symmetry in the other two directions, that would already be a good approximation of what you should expect. So you would think, okay, and this is what Franz was pointing to also last year, we probably think this will go okay. But when it goes okay and when you find it's really robust, then you do it again and you lift it to 2 dimensions. So what you see here is exactly the same situation, but now you have inhomogeneity in 2 spatial directions, that's why the box. And you start again with large shear, this is green, so this is totally dominating the energy density with a non-homogeneous distribution. You have matter being red, this is the scalar field, matter being somewhere low. We start with really low matter density relative to the other energy densities, and we have that curvature, spatial curvature being added. If you run the simulation, you see, it's pretty. So what's really happening is, there's again, everything gets smoothed out very quickly. You see, red wins, and there is no bad region. And we did it for a lot of initial data. So again, just what it means is, this is not something that is not so surprising as the other one was. So going from being close to Friedman, Robertson, Walker, and studying it non-perturbatively, that should have surprised everyone. That it's being so robust that for most initial data, you don't even produce any parts of space-time that end up with mixed master behavior. That's surprising. That now you lift it to 2D and you see this. This is more, okay, we expected that, but it's still good to know. And it's beautiful. So far, so good. And this is so Paul gave me a few assignments to show you from what we did. This is what we call classical supersmoothing, okay? But he said another thing. We, for better or worse, and Alberto is here, who was one of the people who have shown it first, this slow contracting mechanism does not amplify any curvature fluctuations. So the good features of when Slava and Paul and others and Mizau first introduced inflation, then what they figured is the nice quantum behavior of it was that not just you had a looked like a classical smoothing mechanism, you also had a mechanism that induced gauge invariance, so real physical small fluctuations in curvature. And that was, I think, what would be today considered the main triumph of the model. And one of the features of that was so not just that you had curvature fluctuations, you also wanted to have something that's over, so not just a smoothing, the classical smoothing should be on super Hubble scales, but we know now today from cosmic microwave background observations that also the wavelength of these fluctuations that survive the smoothing mechanism should be on super Hubble scales. Otherwise, you would not see this beautiful, nearly scale invariant feature of the temperature fluctuations in the microwave background. So that's what it's reflecting. And so with respect to the wavelength, everything still looks really good and very similar to, in some sense, very similar to inflation. What was great about inflation in this sense, and in some sense, it's very different. And the difference is coming from what Paul explained to you. So if you want to have In inflation, what grows really rapidly is the scale factor. So super Hubble means that while you keep the Hubble parameter nearly frozen, the Hubble radius nearly frozen, you let the wavelength of modes go out of the Hubble patch. And that's what super Hubble means. What here happens in our scenario, the slow contracting scenario, and really I probably cannot explain it as beautiful and Paul did, but what happens is you almost nearly freeze in your scale factor, so the opposite behavior. And so you freeze in nearly the modes. And what happens is you shrink in the Hubble radius on them. So you have in some sense, a complementary mechanism to the inflationary super Hubble stretching. This is super Hubble freezing in some sense. You freeze in the modes, and you shrink in the Hubble patch, which is denoted blue, on them. So far, so good. But what is quantum supersmoothing? So again, it was this, I don't want to make, probably around 2007, right, ago, so short after the ekpyrotic mechanism was introduced. It was also pointed out by Alberto and collaborators, Paolo Cremonelli and Matthias Adriaga, that no curvature modes get amplified. So while the wavelength looks fine, the amplitude, so here it's all about the amplitude, okay? We can have super Hubble wavelength in a slowly contracting phase, but it's not possible to amplify is the amplitude of curvature fluctuation. They decay. And the simple physical explanation is, well, it's exactly the opposite to inflation, right? Instead of having a frozen in, what affects the amplitude is exactly the behavior of the one dynamical scale here. What Paul was also emphasizing in other contexts, the Hubble radius. So in inflation, the Hubble radius is nearly not changing and damping the modes and causing them to have a nearly constant amplitude, but they survive the inflation mechanism. What happens here is you have a rapidly growing anti-friction term, which is now the negative Hubble parameter, and that dilutes everything. So when inflation things were red shifting, here things are blue shifting. So everything that goes into the curvature direction, everything that goes into the so-called adiabatic direction as the background moves, just decays. And that's why we call it a quantum smoother too. So instead of anything surviving, and you should get a little nervous if you don't yet know, is that nothing survives. Not just classical inhomogeneities and anisotropies don't survive. Nothing quantum survives in the adiabatic direction. It's important. Now, you can think of it as a complication to the model, or as I do, you can think of it as an advantage to the model. Because unless you have an idea how to, or you are not bothered by quantum runaway, or some people call it the multiverse effect. I would prefer to call it a quantum runaway. That doesn't happen if you don't have growing modes. So in that sense, it's an advantage. Now, of course, it's a horrible disadvantage if you want to explain the origin of structure. So you cannot be perfectly smooth. If you're perfectly smooth, we wouldn't be here. And in this sense, there is only one option as far as we know. And again, this is all borrowed from the early work of people who worked this out in the context of inflation. There is only one mode that can grow, one type of mode, have growing mode amplitude. Again, it's not the wavelength. The wavelength can be super Hubble. It's the amplitude that's important. And this is the so-called relative energy density mode, or isocurvature mode. So just to recap a little bit. So there are two types of mode, and I was talking about curvature mode, or so-called adiabatic modes that convert, that we need. We know that those are the type of modes that disturb the metric enough that it can induce the origin of structure and then can manifest itself, for example, in the temperature fluctuations of the microwave background. But we also know that there can be, in principle, other kind of fluctuations as soon as there is at least one other matter component. And this is, let's say, if you had a second scalar field. Now, that's not so rare, right? This is typically we assume more scalar fields. And these are these relative fluctuations between the different matter component as the so-called isocurvature fluctuations. And what turns out that they survive. So they can exert the behavior as the inflationary adiabatic fluctuations. Now, there was another hitch to the story first. Of course, when one first looks at the model, one just asks the question, and this is very much was manifest in our last year's talk when we presented the bounds. This is the first question, can I do it? It's usually not pretty. So when you do it first, you just want to do it. If you are very lucky, it's usually pretty, but I would say first you have to know it is possible, and then afterwards you want to figure it, is it always ugly, or can I find some natural mechanism? And here it was exactly the case. So earlier people, what worked out is, well, isocurvature modes can be there. they can be nearly scale invariant. They can survive the smoothing. So these are the only modes that are not diluted away by this extremely robust quantum and classical smoothing mechanism. But they are exerting, because they are unstable, they are in some sense strongly coupled, they exert huge non-Gaussianities. And they are unstable, so if you, and we will get to that, ran a simulation, generically, you would not end up in the state where you would want to go. We don't like unstable models in cosmology, we like attractors. That's why people, for example, like inflation, that is considered an attractor mechanism. And we want to have, so if you ask where you end up generically, you are generically sitting in an attractor. So if in an early universe, you ask, where do I end up with the smoothing contraction if I had a second field generically, you don't want to take a model that's unstable. So we have, it's a long time, so the model is not new, the simulation will be new. We have found a model, and it's been quite a while, 5 years ago, and showed that what was the early problem? What is the reason, again, very simply, the physical reason, it's all about the background. We are in linear perturbation theory, so we know that the background will determine what's happening. So what the case was that how the early approaches made this, added the second field, it just cloned the first field. So you had a field, here's the Lagrangian, it just, you have a canonical scalar with exponential potential, still the same scenario as Paul was presenting you, coupled minimally to the Einstein-Hilbert term, so Einstein gravity, and people just cloned this field, added a second phi, call it phi 2, with the same exponential potential, and that had the same equation of motion. Now, what's really important is recall what causes all the problems in contraction with respect to fluctuations, the blue shift. So the anti-friction term in the Klein-Gordon equation. If the only term that acts on the scalar's velocity is the background, which is the advantage of inflation, we know this is a really disadvantage. This causes the single field adiabatic modes to decay, blue shift, and this causes the two-field configuration to be extremely unstable. You are always on the ridge, so that's not generic. Now, what is the idea? After the fact, you know it's simple. Well, can you add the non-canonical kinetic coupling, a so-called nonlinear sigma-type coupling, to the second field that will be your adiabatic field? Well, you can. And what happens then? You change the friction. You can turn an anti-friction term into a friction term via this non-minimal coupling. It's typically also thought of as an exponential nonlinear coupling. If that happens, that's everything there. Then if you compute the equation of the fluctuations, first of all, you can show that the system, this configuration ready for the background, is absolutely stable. You have the background trajectory almost not knowing, or literally not knowing of the second field, since the stable configuration is when the velocity of this second adiabatic field called chi is 0. So your background evolves, you are slowly contracting into the phi direction, that's your slowly contracting field, and everything what the high does is fluctuating around it, exerting these entropic perturbations. And the configuration is stable because it's, instead of being anti-damped through the background, slowly contracting, but rapidly growing in terms of absolute value anti-friction term, now you are being damped. So this field thinks is actually inflating. The background is inflating in some sense because you have a frozen friction term. So that's all about it. It's a beautiful scenario, has all the advantages. I hope at least a little bit sold it on you. Has all the advantages, so the strong coupling you got rid of, it's a stable configuration. We think it's in the sense least tuned that it's stable. So, and that remains to be shown at least in the perturbative limit, robust to the perturbative limit initial data. It can have nearly scale invariant fluctuations, and due to the absence of any significant mass term in this field, there is also no local non-Gaussian or any other type of significant non-Gaussian contribution. And I should also add, because I was assigned in the previous talk, for the same reason why everything blue shifts, the primary tensor is also blue shift. So generically, just for the same reason why the adiabatic fluctuations blue shift, you don't expect a contribution. So if the Simons Observatory measures anything what they can measure the next 5 years, this scenario is dead. And it's good, because we know that not to follow something that's wrong. And Paul mentioned the secondary tensors. So far, so good. But I don't want to give a talk, obviously, about the relatively old result. Why do I bring this up? Well, on the one hand, I promised you in the beginning of my talk I would show you something that is not surprising, but nice. We can lift something, a mechanism, into a non-perturbative limit, and we see that it's even more robust than originally thought. But I also promised you something else. So it was for me a great learning experience. I myself appreciate nonlinear analysis since then even more. So what you would ask is, okay, this was actually the first project when we started to work with David Garfinkel. Well, look at this scenario. This is the realistic scenario. What do I have from having a scenario which is robust to initial data when I know that it doesn't amplify the abatic modes? So the first scenario is beautiful, it works, but it leaves you with a universe where nothing can happen. So you have to now show that this scenario is just as robust to initial data. It smooths, but it's robust to arbitrary initial data, and it puts you on the trajectory where you want to be in the background. So what you would expect is you start with some initial data, and the high field should freeze out, and the phi field should be growing in magnitude. So you do the simulation again, add yet another equation to that already complicated system. And so I show you what you see. Again, we did it in 1D. It has to eventually be lifted into 2D. But it's the same configuration. You will see again 120 e-folds. And what you see here, this will be the high field, so the entropic field, and this will be the phi field. Now, let's start both of the simulations. Start them simultaneously, if I can. Oh, my thing is vanishing. OK, good. So you see the high field. Whoops. That's vanishing. So it will be now boring. So that looks good. That's the first thing what we see. So it looks like that it went down. In the phi field, you see it's picking up on volume more and more and more and more. That won't make Qumran happy because it's like growing like crazy, but it's just for the classical analysis. So it's not a realistic scenario in the sense of the only thing what I want to demonstrate to you is exactly what you expect. So you do the analysis, and it's boring, right? So OK, carry on 120 e-folds. But it looks like that we were really good about the perturbative limit. Not much happened. So you basically want to see now what I hope you want to see what happens to the omegas, right? If I can move on to the next slide. OK. So now so the fields are, that's what you would have been mostly interested in. We actually know how it is. Once a high field freezes out, what we would expect is we have just the apparative one-field mechanism. It's just robust to initial data, and that's what we will see. So what you would expect is if we start with large shear, significant spatial curvature contribution, and some matter density, then we will end up just what we saw in the one-field mechanism. It must be the case because the high field throws out, right? OK, so let's do it. Looks good. See, matter went up. Oops. Well, what's that? Right. That doesn't look good. So this looks pretty bad, right? So you have now several choices what you can make. I intentionally show you a code that doesn't correspond to the mechanism. I can show you a code that has a bug. No, neither of those. Or this is really what's going on. It's actually really what's going on. So we would not have expected that. So the Robertson-Walker space-time is not a good approximation once you have the second field added. Even though the scalar field freezes out, and I'm only on one slide away from the end, so only the scalar field freezes out, the velocity freezes out, phi behaves exactly as it should, but for some reason it's not smoothing. What you end up is actually, and I didn't talk about that too much, but I should mention it, what it is, because it's notable. It's a so-called Kasner space-time. So it's a homogeneous but anisotropic space-time where you have significant contribution from the shear. So it looks like a constant shear, and a constant scalar field matter density. So what went wrong? Why is our, I mean, it's a puzzling scenario, right? We think that the only thing what we need is to have a so-called slowly contracting background, the high field frozen out, that cannot really contribute to the energy density. So how can it induce nevertheless shear? It doesn't come out of the analysis that we are used to. We assume Friedman-Robertson-Walker space-time, make sure that it's self-consistent, and then make sure it's a tractor, and then we know what the indicators are that it should be like that. Well, the reason is that you can just get as far as being around FRW as you are in a perturbative limit. But what if the assumption was wrong, that that's the attractor solution? then you have to go back to the full set of equations and try to figure which is the term that caused this. And now you can imagine, it is quite surprising. We are ending up with a constant gradient term. And there is a physical reason, or there is a reason in theory what causes it, but just let me explain why it's the reason. Now, notably, we know that Einstein relativity is such that you can write it in a formulation, and this is, I think, the simplest way to understand this, where everything to leading order in derivative takes the form of a wave equation. So we have the two scalar fields have a wave equation, and the metric follows a wave equation. Now, what happens in particular case of the scalar field is that if you have a shift symmetric Lagrangian, constant gradient or no gradient are almost just as good. In particular, it turns out that no gradients are no attractors. The constant gradient is an attractor due to the shift symmetry. So what causes this mess is that you actually were not supposed to be doing the expansion on FRW spacetime. You have to find the solutions. You didn't perturb around the correct solution. The correct solution was a constant gradient, and this is what it was not trivial. We tried everything until we figured, oh, this is actually a shift symmetry. The shift symmetry tells the theory that your constant gradient solution is just as good, actually better. That's where I want to be, instead of where there are absolutely no gradients. So what do you do? And this is really, I think, this is a real learning curve or learning effect, because doing the non-perturbative analysis actually taught us something that we would never have thought we need to learn. Okay? So we learned something that we would have not seen in a conventional way, and where it leads us is how to build a Lagrangian. So, oh, this is not doing again what I wanted to do. So I show you something, same configuration almost. And I evolved this simulation. What happens here? Well, it looks good. So I changed something. We changed something. So we learned something. And obviously, I almost gave it away. What we changed is we broke the symmetry. So what we knew from the earlier study, it's actually in the paper that I showed you in 2014. So if one works with a student, then the student usually knows better to do things than a postdoc, and I was then a postdoc, and I worked there with a student called Aaron Levy, and he said, well, I want to do the most generic analysis. Let's see how far we can get with this configuration. And he showed, well, actually, the spectrum is just as good when you have added a little mass, what would be the most natural thing to the high field. So you can, because the high field, due to the damping, what happens is, I made a big point of the wave equation. Because the high field follows a wave equation, the nonlinear sigma type coupling only damps the kinetic energy. It doesn't damp the gradient energy. It only sees the second derivatives with respect to gradients. And that's why you end up, due to the shift symmetry, with the no mass, with the constant gradient term being the true attractor. So if you do what you should have done from the beginning, and what Aaron pointed out, I completely give him the credit on this one, that if you had a tiny mass, but of course, massless fields are just a lot less. It's almost unavoidable that any field has some mass. A tiny mass that almost immediately breaks the symmetry doesn't make any difference to the perturbative analysis what the spectrum will be, because the high field is being damped out by the nonlinear sigma type coupling. But what it does is it completely changes the attractor behavior of the background. And that's why you end up here with a completely smooth background where there's absolutely no shear contribution at the end, and you have the same desired behavior because you broke the symmetry, and now the system knows where to go to. So this is not something we could have done and would have figured. And so we used here the non-perturbative analysis to eliminate a huge family of Lagrangians and end up with a very concrete family of Lagrangians that we can study if we want to be generically robust to initial data. So I really like this because it was so counterintuitive, and I think it's a really beautiful demonstration that relativity can even contribute in cases when we would not expect it, in the sense of a nonlinear analysis. So, and this is really the main message, what I think Franz will continue on tomorrow, and where we also continue on, we know that whatever we conclude in the perturbative regime, how good our bounds can be or not, that will be decided once we do the full study. And this is also where I should and want to stop. Thank you.